My sound is selected. Okay, in the previous class, I have shown you that for different geometry, you will have a different drag coefficient, especially at a high Reynolds number. Okay. You know that at the low Reynolds number, low RE, shape is not significant. It's not significant. But Reynolds number, Reynolds number is significant, but your shape is not. Okay, so as shown in here, when you have a creeping flow or low Reynolds number, doesn't matter how is the orientation, you will get all the CD is a function of Reynolds number. This one is 24, this one 22.2, this one 20.4, and this one 13.6. But when the Reynolds number is increasing, when you change the shape, let's say the hemisphere, you put it on the forward and backward, it will give you a totally different CD. Okay, this one has a 1/3 lower CD compared to this one, right? And then we have also learned for some geometry, the CD is given in this table. Okay, if you ask me, do we have it if we need it in your exam? Yes, you will have it. Okay? I have told you the principle is all the required information will be given, but not all the given information is required. So you need to choose. Okay, don't ask me which one to use. That is your problem, not my problem. My problem is giving a question to you complete with the data, I give it you. Okay, that's it. No question during the exam. If you want to ask during now or during the tutorial. Okay, and you need to remember for this finite cylinder and the sphere, okay, this thing is applicable for limited Reynolds number. In this case, this one is only for laminar flow when the Reynolds number is less than 200,000. Then what happens if it is more than 200,000? You cannot use this anymore. You will use the next one. The same goes for that. What happens if it is more than that? Then you cannot use it. Okay. As of car, I have shown you that some car has a very low drag coefficient, especially the XL1, which has 0.11, and then the Rodua Beza is what? Relatively low coefficient of drag. Okay. Now we would like to see what happens if we have a cylinder but the Reynolds number is more than 200,000. Okay? If you have done your assignment 2, there is one question that you will need the information of this. Okay? Here, in your assignment, you will need to use this one and that one. You see there is a nameplate and the air is coming through it. Then you need to calculate the drag force need to hold that board. So you will need to use those things. Okay. So before we go to that, let's take a look at what happened in the flow over a cylinder. Okay, you will find this one again when you take heat transfer. Right? Next to semester, you will see exactly the same like this again. If the lecture explained to you, if they think that you already have it, they will skip this one. Okay, so at a very low Reynolds number, the flow is primarily due to the friction, right? And you can see that the flow is basically hugging the cylinder. You do not want to split with that, so it just goes into the cylinder, make a contact, and then flowing over the cylinder in a nice manner, like you just slip over it. Okay, there is no spiration, no nothing. When you increase the Reynolds number, spiration start to occur. Okay. When you have a free time, you are in a low pace, right? You are in a good term with your friend, everything working smoothly. Same with this, right? The flow is moving smoothly. Okay? When quiz 1 takes place, you start to be in rush, your pace is getting higher, you start to get inspiration. You cannot meet your friend again. Right? Sometimes you need to work on your own, sometimes your friend needs to work on your own. So spiration is there. Close to the test, you start to get argument with your friend. So you have a bigger spiration. You do not want to be in one room anymore. Okay? Your friend will work in IRC, or if you study in IRC, you will study in Surau. So these things will occur, right? This will create the oscillation. This oscillation is called von Karman vortex, which means the flow is no more attached to the. Okay, so this one will detach and it goes there. At the other time, this flow will detach and it will goes to the other time. That's why you get this kind of vortex, and this vortex is called von Karman vortex, right? As it goes further, the turbulent boundary layer will occur and you will have this spiration zone, which is very clear, right? On this point. So you can see the flow is detached from the surface and it goes creating a wick. So this one is called the wick. The wick, right? Wake up. Vortex wick. Okay. Interestingly, if you have a laminar boundary layer, if you have a low Reynolds number, I mean the Reynolds number is high enough to create the vortex, but it is not high enough, right? It is just enough to create this vortex. You will see that the spiration zone will start early in this region, right? In this region, you start to have a detachment of the flow. But when you have a turbulent, the detachment starts at much later stage. You can see this one, the detachment point is over there, but for here, the detachment point is over here. What does it important for is later on you find out why the golf ball have a dimple is because of this. Because of this case. Right? So let's take a look at this one. This is the correlation or the chart for the sphere. And so this one is the sphere and this one is for the smooth cylinder. So in the creeping flow, okay, in this region, you see that the drag coefficient is a strong function of Reynolds number. Right? This is as it goes further. In this region, this is your bluff body characteristic. This one is the one that you have in the table. So the value you have in your table, L over D equal to blah blah blah, is actually only representing this region. What happens if you have a region beyond that? You cannot use that table anymore. So you need to use this one. Okay? And this is the interesting part. This is the interesting part. If you have good understanding on it and somehow you manage to design something that has Renault number in this region, okay, the good thing is you have a sudden drop in the drag coefficient, which means in this condition your drag can be minimal, right? But if you wrongly design it, rather than putting in here but you put there, it will start increasing it. Okay, so this is the condition that you must get if you want to minimize your drag, because the drag is very low in this region, right? Both for smooth cylinder and smooth sphere. Okay.